So today we just have some function practice. We just got a few code along projects to go through. Apologies, I don't have the slides posted in GitHub yet. Those will be up after class ends today. But that's okay. I will just present from, okay, come on. I'm just trying to, oh my gosh. Trying to select this border here. Let me grow this window size a little bit. Just maximize that. Okay. Get things oriented here. Whew. So yeah, today's just a code along. So get your REPLs ready, whatever your coding environment that you like to use ready, and we'll go from there. All right. So this is sort of an iteration on the theme from yesterday. We're going to be building a PMF. Yesterday we did a like a class, quote, class object-oriented breakout, where we kind of did some of this stuff, where we did a problem that looks a lot like this in an object-oriented style. And we'll do this in a more traditional style, or a more kind of functional or procedural style this time. And it'll be a little bit of a compare and contrast with yesterday. Squeeze that in. Okay, so this is just talking about the, giving us an example of the CDF of the binomial distribution. So it's always good to reinforce this stuff. It's going to, be pretty central in the DSI, having a strong understanding of stats and distributions, obviously. So can't code it out too many times. So remember the PMF for our binomial distribution. Let's now create a function that will return the CDF of the binomial distribution. A problem for CDF might look like, suppose you have a fair coin, meaning you have an equal probability of either heads or tails, and you flip it 10 times. What's the probability that there will be 6 or more heads as a result of 10 flips? So we want to represent the below equation in Python, where n is the number of trials, k is the number of successes, and p is the probability of success in each trial. So your fair coin, you flip 10 times, what's the probability that there will be 6 or more heads as a result of these 10 flips? Let's think about this problem first. Let's say success equals heads. We'll just you can pick an arbitrary success case. Success has, I think it's easy to connotate a meaning to success, but it's just an arbitrary case, not even just for a coin flip, but it's important to think about, quote, success in the context of binomial, as it's denotated, as the denotated meaning in binomial rather than its connotated meaning. So what do we need in order to perform this problem? So we can read through this. We've got a few elements in here that are sort of easy to translate into code, right? What do you think of when you see a sigma? So we've got the sigma, which means the sum from I starting at 0 up to k, summing all the results of n choose I times p to the I times 1 minus p to the n minus I. So what's that sigma mean? How can you read that sigma and translate it into Python? Go ahead and put it in Slack. Get a few answers in here. Sum all. Yep, what's our sort of go-to mechanism for summing or collecting elements from a collection? Cool. For loop, yeah. For loop from 0 to k accumulator. Yeah. So when I see a sigma, I think of a for loop running through usually a list or a range, summing all the elements generally in a numeric accumulator, i.e., an int or a float. So I think of a numeric accumulator pattern. So this is kind of cool because if we can implement this in choose I times p to the I times 1 minus p to the n minus I, if we can implement that formula correctly, then we can just take the sum of those for various values of I in range 0 to k inclusive. So cool. So that I just kind of wanted to reinforce that when you see a sigma, you're generally running through a for loop through a range or sometimes a list. And this is just giving us our binomial PMF. But let's actually, I'm going to kind of go off script a little bit here. In order to write CDF here, I'll scroll up. In order to write CDF, we need our PMF, right? So if you look to the right of the sigma, here is actually our PMF formula, right? And you can plug in, instead of I, you can plug in K. It's usually tradition, but either way, it's still the same formula. In choose K times P to the K times 1 minus P to the N minus K. So that's our PMF formula. So we need this in choose I bit, which is generally known as, you saw it down below, but just in case you didn't see it down below, put it in Slack. What's the formula for the choose? Or what's the other name for it, is what I'm trying to ask. When we do in choose K, what are we trying to do? Hashtag combinations. Yeah. Answer in hashtag form. Those are the acceptable answers. No, I'm just kidding. So combinations. So that's our combinations formula. And what do we need? There's another formula that we need in order to build combinations. So what's that other formula that we need? Hashtag factorial. Cool. So this is, so you probably have heard me say in passing something about like working backwards or working from like end to beginning. There are times when this is useful, right? To sort of figure out what you want to end up with and kind of trace your way back to where you need to start, right? So this is, I would say this is one of those times. It's, obviously not the only thing you do. Sometimes you work forward, sometimes you start where you start and you work towards your goal, but sometimes you know where you want to end up, you know what your goal is, and you have to kind of backtrack to where you want to start, right? So it's good to just keep that in the back of your mind. When am I backtracking? I have a clear idea of where I want to end up, and then backtrack, right? So this is one of those times, and it shows up in various places, and it's just something to kind of think about. What we want to end up with is our binomial CDF. And in order to do that, we need our binomial PMF. And in order to do that, we need our combinations. And in order to do that, we need our factorial, right? So we kind of work our way back from there. So I'm going to start at the top. Now we'll work forwards. Let's get a working factorial function. I'm just going to hammer it out. It's a simple one. You can race me, see if your typing skills are faster than mine if you want. Which they might be at the rate I'm typing. Okay, let's test it, make sure I didn't make any mistakes. Factorial. Factorial of 4 will be 24, 5 will be 120. Let's try it out. Good, okay, so that's a working factorial function. Leave our tests there. Combinations. So who remembers our combinations formula? Give you a second for this one. If not, no big deal, but I want to give folks a chance, if you have a memory of how to do it, to get those in there. Cool. Yeah, we got some answers. All right. So our combinations formula is n factorial over the product of n minus k factorial times k factorial. So n factorial over n minus k factorial times k factorial. Excuse me, I should call this r. It's a bad habit that I call that k. I should really call it r. Not that it really matters, I guess. All right, cool. So we'll say def combinations. Combinations will take in n and r. And we'll return factorial n over, and I'm going to use ample parentheses. Not that I need it in this case, but it's not going to hurt me, and it's going to make my code clearer. At least in my opinion, it makes the code a little clearer. So you do you, but if you want to err on the side of more parentheses, you'll probably be a little safer. Have a little more consistent results in general. See, I'm saying K, I need to say R. Okay, cool. So n factorial over factorial n minus r times factorial r. Cool. And let's just test that real quick. Print combinations, and I have in memory, I know if I get combinations out of groups of 2 out of 10 objects, I should get, I think, 45. Yeah, 45 for combinations. Cool. That does return as a float. It'll only give me whole numbers back, so I'm just going to cast it as an int right in there. So combinations will always give me an int back now, which is kind of nice. Let's see. Okay, sorry, I'm trying to just adjust this a little bit. Okay. All right. So our PMF. So we have our PMF formula right here. So we'll just do def binomial PMF. We'll take in n, k, and p. I'm going to default p to 0.5. Yeah, so then we'll say return, and then we just implement the code to the right of the sigma here, and that's our PMF. So that's combinations n choose k times p to the k. And I'm just replacing I in the formula shown here with k times, this will be 1 minus p to the n minus k. Cool. All right, so let's just test this out real quick. We have 10 events. We want to know the probability of 5. Let's just do a few tests here. We'll do one for 4, one for 5, and one for 6. And we should see 5 at the peak, and 4 and 6 should be even with each other. Oops. Yeah, so 0.205, 078, 125 in either case for 4 and 6. And then PMF of 5 is a bit higher than that. Cool. Looks good. So I'm just showing you those kinds of things because I want you to, I want to give this a little airtime. You know I talk a lot about testing, but I think some folks need to hear it more than others. Let's just kind of clear this out a little bit. So it's always good to think about, well, if this is working, maybe you don't know what the PMF of 10 and 5 should be off the top of your head, but you can think about it and you could say, well, the pattern, there should be a certain pattern at least, right? There should be a pattern of, intuitively, you can determine if I flip a coin 10 times, what's the most likely result? You can think about that. Well, the most likely result would be 5. So, what would the probabilities of 4 and 6 be? Well, they'd be even because since we have an even probability of success, the probability of getting 4 successes and 6 failures is just it's saying the same thing in this case as getting 4 failures and 6 successes. So think about those little patterns and always give your code a good test. I wanted to bring this up. Somebody brought it to my attention that I made a mistake in the Poisson class that we wrote yesterday when I did from math import e as e, and then when I implemented the function, I wrote lowercase e instead of uppercase e. So I specifically named it uppercase e, and then I forgot to use it as uppercase e. So I didn't test my code that time. I just kind of wanted to, it was similar to the previous class, and I was like, it'll be fine. But I made a mistake and didn't catch it. So that's why it's always good to test your code. Think about patterns, even if you can't triangulate an exact result, think about how you can determine if something's still working correctly, right? Yeah, cool. All right, so on to our CDF. So our CDF, binomial CDF, will take in N, K, and P again. We'll default P to 0.5. And we'll say, all right, ACC. So this is just a pretty vanilla accumulator pattern. ACC equals 0, and we'll say, see, CDF, thank you. All right, so this is our CDF. Somebody pointed this out, thanks very much. As I'm talking about mistakes and misspellings, right? Typical, but so this is just a vanilla accumulator pattern. By vanilla, I mean we've got an integer up top, starts at 0, nothing fancy there. 4 I in range, just a simple range, we'll do, oops, excuse me. We want to include 0, so we'll do 0 to k, and we want to include k as well. I don't need to explicitly write 0, but I don't know, feels right in this case. It's up to you. And then we can say ACC plus equals binomial PMF of n, k, oops, n, I, and p. So we'll pass n and I directly, or n and p, excuse me, n and p directly into binomial PMF. Those just get passed through. And then we'll use k as the limit for the range of the for loop, and we'll pass in I where we would have passed in k for the PMF. And then after we're all done, return ACC. I hope y'all are getting the picture. I tried to make this clear early on when we first covered accumulator patterns, but do you see how often we use accumulator patterns? They're very common, so it's good to be familiar with them. Oops. Let's have a test here. Binomial CDF of 10 through up to 6. Okay. Let's do one of 10. This should just be 1. Cool. Okay. Looks good. All right. I'm just going to kind of scan through this real quick. This is talking about the CDF code. Cool, and let's look at the code they wound up with here. So factorial combinations, PMF, CDF. Yeah, this is exactly the same as what we did. Okay, so now let's visit the problem. We started with suppose you have a fair coin. I think I just did this one in my test here, right? Suppose you have a fair coin and you flip it 10 times. What's the probability that there will be 6 or more heads as a result of those 10 flips? Oh, excuse me, 6 or more heads. Aha. As a result of those 10 flips. What would be our answer for this? Remember what the question is asking for. First, call our binomial CDF function from 0 to 5. And we know that the probability of getting 6 to 10, we can think about the probability of getting 0 to 10 is 1. And that's what this tells us, right? This one gives us 1 back. So since that's just 1, the probability of literally any result is 100%. Like you're going to get one of those results. You're going to get some number between 0 and 10. So we can just assume that that's 1, and we can just subtract the numbers that the range that we're not interested in, right? So we want to know the probability of getting between 6 and 10. So we can say 1 minus the probability of getting between 0 to 5, right? So 1 is the probability of getting 10 through 10, right? Which we can pop in there. That's going to give us 1. So this minus 0 through 5. And that'll give us 6 through 10. Cool. Does that make sense to everybody? Hopefully it does. And this is just an example of that, right? Another way of doing this is the probability of 10 to 6, 10 to 7, or excuse me, the probability of getting exactly 6 plus exactly 7 plus exactly 8 plus 9 plus 10. It's the same thing. When you're actually coding this out, you could do something like lower and upper, and plug these in as your ranges here or something. And then you could have a CDF function that would take a lower and an upper bound. There's ways of doing this where you could do it like range. If you use star args, and if you use star args, you could do it where it takes, if it takes one value, it'll go from 0 to that value, and you could have some other logic in here to kind of deal with that. But this will just take that, and we'll have to calculate our lower bound like this, which is a little funky, but this is sort of the traditional way that this is built. So that's how it is. All right. So you got a few little kind of breakouts here. So let's use our function to answer the following problems. So an article, should you report a fender bender from Consumer Reports in September 2013, reported that 7 in 10 auto incidents involve a single vehicle. So disclaimer, this article recommends that any accident involving one vehicle should always be reported. Suppose 15 accidents are randomly selected. How would you call the function to get the following answers? So let's look at this. This is kind of nice. You see me go through this. I like to do this in my text editor, just kind of lay out information and chop it up. And I'm looking for this sort of important information, input, process, output. In this case, I'm looking for the elements, the inputs to my binomial CDF function. What are my inputs? It's the number of events, the probability of success, and the range of success cases that I'm looking for, right? So I'm just going to chop this up in here and kind of show you how you can do this, right? So let's use our function we created to answer, should we report a fender bender? Okay, so we'll delete that part. So from Consumer Reports, September 2013, reported that, I'm just going to pare this down, right? So it says 7 in 10 auto accidents involve a single vehicle. So 7 in 10 auto accidents involve a single vehicle. So what does this tell us? This is useful information. 7 in 10. This gives us one of our inputs for our binomial CDF. I'm gonna try to, there's some of the answers are down here, so I'll try to pretend like you didn't see those. Ignore the man behind the curtain. So what piece of information does 7 in 10 accidents involve a single vehicle? What piece of information does that represent? %, or a 0.7 probability, yeah. So this is our P, right? So I could say P equals 0.7. Cool. Suppose 15 accidents are randomly selected. How would you call call your function to get the following answers, and those are below, and we'll pull those in a second here. So 15 accidents are randomly selected. What does this number represent? Sorry, if you could hear me drumming, I realize you could probably hear me doing that. Cool, yeah, so this is our number of events, which is our n, right? So this will be n equals 15, right? We don't have a k in here yet because that's going to come later, right? That part will come when we ask specific questions, right? But this sort of lays the foundation. N and, well, P especially is really kind of a, for a given topic, for a given thing that you're analyzing, your probability of success is basically constant. Your number of events is subject to, your particular implementation of the experiment. And then K is sort of supplied when you're asking specific questions, right? So P is basically constant, N is kind of a constant, and then K is more variable. At least that's the way I think about it. Okay. Don't do that. Okay. So I don't know, the answers are kind of right here, but we'll pretend like they're not there for now. Okay, so what is the probability that exactly 4 of the 15 randomly selected accidents involves only one vehicle? And you think about this. How would we calculate the probability that we'd get that exactly 4 of the 15 randomly selected accidents involves only one vehicle? So remember, here's another piece of useful information. What is our success case? What is our success case? So our success case is an accident involves only one vehicle. So that's our success case. So what is the probability that exactly 4 of the 15 selected are successes? So what's the probability of exactly 4 successes out of 15 events? Exactly 4, so Pmf with a K of 4. Yep, cool. Who wants to show me some code? Okay. All right. We got something. Cool. All right. So yeah, that'll be our binomial PMF with n equals 15. And we don't have to do the keyword args like this, but I'm going to do it just because I don't know, it's nice to be clear. K equals 4 and P equals 0.7, right? And just to be clear about what I meant by that, we don't need the N equals and P equals and K equals stuff. We can just do this, but yeah. Let's run that. Okay. Oh no. I wish that I gotta go in to delete those answers from there. Kind of makes it silly. Okay, here's our next question. And here's our probability. Okay, what is the probability that fewer than 4 of the 15 randomly selected accidents involve only one vehicle? So think about this one. Think about what code you would write. How could we use our functions to determine this? We got a question here. Does the argument 0.7 override the parameter p equals 0.5 in the function? Yes, indeed it does. Yeah, so that's actually a good question. If I just pass in a 0.7 here, this default just allows me to not pass in anything, and if I don't supply a value for p, it'll just say, oh, okay, well, since I didn't get a value for p, I'll just assume to use the default of 0.5, but I can override it by just passing a third argument, and that'll act as p. Excuse me. Okay. Okay, so what is the probability that fewer than 4 of the 15 randomly selected accidents only involve one vehicle? So that's 0 through 3. So what might we use for that? Mm-hmm. Excuse me, I got a little itch in my eye. K equals 3. Yep. K of what? What function should we use? CDF? Yep. Cool, so that'll be our, I'll just appropriate this one. CDF 15, 3, and 0.7. Cool. All right. Don't look at the code. Okay. Okay, cool. So here's another one. What's the probability that 10 or more randomly selected accidents involve one vehicle? So it's another way of saying that. What's the probability that we have between 10 and 15 successes? 10 or more successes. One minus the probability of 9 or fewer. Yep. Yeah, you could think about it as 1 minus the probability of 0 to 9, right? So that's 1 minus 15 to 9. It's the complement of 0 to 9. Cool. Okay. And finally, what is the probability that more than 5 and less than 8, so between 5 and 8 of the 15 randomly selected accidents involve only one vehicle? So more than 5 and less than 8. That's the sum of the PMFs with k values 6 and 7, right? This is a little bit tricky, but it's not going to include the 5 and the 8 in either case, right? So one way to do this is we could use our PMFs. We could add the PMF of 6 plus the PMF of 7, right? It's one way to think about it. But we could sort of make this a little more generic. Let's say low, let's call it lower LWR and upper UPR. So we'll say lower equals 5 and upper equals 8. And we want to use PMFs, or excuse me, CDFs. So we could say, oops, I have to actually have an equal there. So how would we use CDFs to do this, right? So we could do the CDF of upper -1, upper -1 to lower +1, because in either case they're excluded, right? More than 5 does not include 5, less than 8 does not include 8, right? So we can do this. It's a little funky, have that plus and that minus thing there, but oh, excuse me, that should be minus, not plus. What am I doing wrong here? I've made some kind of error. I want to keep lower? Wait, am I crazy? Okay, I want to keep lower. Okay, brain fart moment. Cool. All right, thank you. Got carried away with the modifying there. Cool. All right. So we could plug in different values here and essentially use this as a way to calculate the probability of any range, lower and upper. Okay. We've got another breakout here. We're about at the halfway point, so I'll be merciful this time. Let's have a full 5-minute break. So let's reconvene at 2 minutes after the hour. And I actually mean 2 minutes after the hour this time. Cool. All right, we can get going again. 1 second. That'll be that. Let me find where we left off here. Cool. All right, so here's our second breakout. I like this problem. This used to be part of our old, long ago, part of our old technical interview. We'll say the technical interview has changed quite a bit, but yeah, I don't know, it's a fun problem. So let's create a function that takes a list of words and returns a new list of words that are anagrams of each other. So for example, dog, god, cat, act, tack, star, rat, rats, right? So this will return dog and god because they are anagrams of each other. Cat and act are anagrams of each other. Star and rats are anagrams as well. Notice rat is not in there, even though rat has all the letters that are in rats, it's missing the S. So some people have asked me what an anagram is. It's not to be mistaken with a palindrome. A palindrome is a word that is the reverse of another word. So like, oh, I can't think of any palindromes that aren't long. Yeah, so it's just essentially the reverse order of a word, right? An anagram is a word that contains all of the the reverse of itself. Yep. An anagram is the word that contains all the same letters, not necessarily in reverse order, right? So if you look at cat and act, CAT is spelled backwards is TAC. It's tack. But act is not in reverse order. It just has the same letters. So any word that has the same letters, that's not exactly the same word, right? So we could do a version of this where, and I'll add that in at the end. Like if we had, let's say, just tack, right? If we had tack in here twice, it shouldn't show up in the return because it's you know, a word, we won't consider a word to be an anagram of itself, right? And that's going to be an important part of this. A man, a plan, a cat, a ham, a yak, yeah, a canal, Panama. Yep, exactly. Y'all get it. I do love the oh, nice, that's cool. I bet everybody knows that palindrome there. Okay. Cool. All right. So let's go on with this one. So I'm just going to steal these inputs, and apologies that I didn't get the code posted yet. So let me just paste in the inputs into Slack here real quick. Expected return. Cool. Okay. I'll just paste those in for myself. So you can go ahead and just paste those in. So this is sufficient information to build a test, which y'all know how much I love those. And we got to decide what we're going to call our function. So I'm just going to call it anagrams. We'll take in my list and we'll return the list below. Cool. So let's def anagrams here. Def. We'll take in a list and we'll have, I'm just going to call it ACK list for accumulator list. I should give it a better name than that. It's going to be a list of anagrams, so I'm going to call it anagrams. Anag. That's good. I'm lazy. Return anag list. Okay, cool. So I'll just run it, make sure I don't have any syntax errors, ready to go. We'll get an empty list and return it. Okay. So who has some ideas how we could start this one? I want to kind of brainstorm this. If string equals string, yeah. There's something there. Iterate over the list. For each element in the list, check it against other elements in the list. Yeah, exactly. I'm seeing some good brainstorming. If the list includes the reversed version, it's a thought. Add it to the output list. So remember, it's not just the reversed version, it's the same it's the same letters in any order, including reversed, right? So we could do that as a particular case. But think of ways, you know, like, yeah, think of ways to compare letters in a word. Add output list, not reversed, same letters, same len. A lot of good thoughts here. Got it, still in palindromes. Yeah, that's fine. Yeah, no worries. We talked more about palindromes than anagrams, so that's on me. Palindromes are fun though, so. Compare characters. Sort them, I missed it. I don't know how I missed that. Nice, yeah. A lot of good brainstorming happening here. Lots of good leads. Cool, okay. So think about the problem. How do we approach this? What are we comparing? How do we compare it? What are we comparing? How do we compare it? That what are we comparing to what? So we're comparing each item in the list to every other item in the list except itself. So if a word is equal to itself, which it is, as words are apt to be these days, then we don't want to make that, we don't want to, we can just kind of ignore that case, right? So if the words are different, they might be anagrams if they're a different initial word. We don't consider a dog an anagram of dog. It's just the same word. What does this look like? Yeah. Cool. So how do you compare, the question is, how do you compare every word in the list to every other word in the list? And I saw some good stuff. I want to kind of pull out some suggestions here, but feel free to, so the question on the table now for you, put this in Slack. How do you compare every word to every other word in the list? And for now, don't worry about, you know, if your answer to that ends up in comparing a word to itself, you know, we can handle that as a case, you know, we can get to that in a second, but how do we compare everything in a list to everything else in a list? Iteration. What's that iteration going to look like? I'm looking up here for a suggestion that I saw. Okay. Okay. Oh, we got a taker. We got a good suggestion here. Cool. All right, so we got a suggestion. And this answers kind of one of the other questions too, is what do we call the elements in the list? And this is what I usually do, word one and word two, as is in the suggestion, right? So this is an odd nested loop, right? So we'll say for word one in list, for word two in list, right? So we have two pretty similar loops. We're just naming the identifier differently in each case, but we're iterating through the same thing. And this is This feels weird, but it's totally legal to do. It's fine to do in Python. So so how does this help us? This is what we need to do. But what can we do now that we have word 1 and word 2? We need to compare them. So how might we start doing that? And also, we could think about it like this. What are the terms of the comparison, right? We know one thing is they can't be the same, right? So word 1 and word 2 can't be the same word. So they can't be equal. So what else? Yep. Somebody's suggesting that we say if word 1 equals word 2, continue, which will just skip the rest of the loop. I'm going to do a slight variation on that, but yeah, you could do that. They have to be the same letters. Yep. And somebody had a suggestion for this, how to see if they have the same letters. In this case, I mean, yeah, I mean, ultimately, yeah, we should probably account for case. In general, yeah. In this case, we'll just assume user responsibility, and we'll assume that all of the letter, or all of the strings in the list are lowercase. So, but that's good thinking. And if you were actually implementing this in the real world, right? So if the character in word 1 equals the character in word 2, that's the thought. Do a character-wise comparison of the two. I think it would be possible to do something like this, like, but it would involve other loops and other logic as well. Compare the sorted versions of word 1 and the sorted versions of word 2. Cool. Yeah, this is the idea that I was looking for. And somebody else, we've had 2 people suggest, I believe 2 people, sorry if somebody else suggested that before. Is this an index problem with enumerate? This won't be an indexing problem, or we won't use enumerate, but it's good to be thinking about it, thinking about like what tools you have access to and what things you might use. So the idea I was waiting for is the sorting idea. So a couple people suggested this, at least 2 people have suggested this. So they have to have the same letters, which we can determine by comparing compare the sorted versions of each word. And if we sort each one, what that does is it orders them in the same, right? So this also preserves the number of each characters, right? So like like DOG and DOGG or OGDD or something like that, they contain the same letters but different amounts of those. And if we sort those, we'll see, you might say, well, they'd have the same letters, but they don't have the same amounts of those letters. So the comparison wouldn't work. So sorting is a pretty robust and simple solution. Okay. Yeah, that'll do for now. So this is our criteria. So the word 1 and word 2 can't be the same, and they have to have the same letters, which we can verify by comparing their sorted forms. There's another step we can take, but it's sort of secondary to these. So we'll start with this and go from there. So one person suggested that we compare word one and word two like this. If word one equals word two, continue. I think this is what they do in the example of this one, if memory serves. What I'm going to say is if they're not equal, oops. If they're not equal, then I'm just going to continue my, writing under this loop. So if they're not equal, then I can go on to comparing them, or actually comparing their sorted forms. So if word one not equal to word two, if the two words, their starting versions are not equal to each other, and if the sorted version of word one and the sorted version of word two are equal, what else might I want to do? So what do I want to do if the sorted versions are equal? You want to append, yeah. Check if you already add the item to your list. Aha, yeah, that was the third criteria that I was going to get to here. But we'll start with the append, and then we'll look at that in a second. So we'll append to an list dot append, and then from here we can just choose word one or word two. I'm just going to do word one, and let's take a look. Oops. I have an assignment, not an equality operator. All right, so I get dog, god, cat, act, star, rats. Let's just compare that to my expected output, and that's the same, right? So somebody suggested that we make sure that it's not already in the list. In this case, we're going to be okay, but because we don't have any duplicate items in the list. So let's make another test, or I'll just reappropriate this test. Let's add dog in a second time, right? So let's see if that changes. What? Oh, I was like, wait, what happened? But I forgot to put a comma in there. I'm surprised that worked. That's extremely weird. Huh. Okay. So we have dog and god, and then god and dog. So since this has, in either case, dog and god can be compared to two things that are not themselves, they'll both end up in there twice, right? So each of these dogs can be compared to God, and God can be compared to each of the dogs, right? So that's why they both end up doubled, right? So it's sort of a double problem there. So we can, to prevent that, we can make sure that word one, which is the word I'm adding, is not already in an egg list. So I'll leave it to you all. What line of code would I use to ensure that? If ... not in ... Yep. if not in. Yeah, that's a start. So what do I want to put in the dots? I mean, I think y'all got it. Yep. So that'll be if word one not in an a list. Then we'll add it in. So now let's see if it fixes that duplicates problem. Cool. Okay, so we have the correct list again. And let's see, just because I gave this example earlier on too, let's duplicate tac in here, and that should also not be added in because it's just a duplicate of itself. So that'll prevent duplicates as well. Cool. Just a quick note here. You'll develop an eye for this as time goes on. There's a rule in Python that you may have heard. It's kind of a what do I say? I say it's a rule, but it's a formal convention. Oh God, I can't remember where this is from. It's like the Zen of Python. There's all these like kind of funny Python pros that are out there, and I think this is on the official Python website. It has some little pros about how flat is better than nested, and this is pretty heavily nested code. So we can do a little bit to clean this up. This works like intended, but we can do a little bit to clean this up. So when I see an if that contains only another if, right? So the body of this condition is it contains one thing. To me, I look at this and I say this contains only one thing. And if that, which is this if, which happens to contain another if, which happens to contain code, but I don't consider this 3 lines inside of this first one. I consider it one line essentially, which has a body, right? So in this case, if you see an if that has only one thing and that thing is another if, you can translate that into and, right? So I can say if word 1 not equal word 2 and sorted word 1 and sorted word 2, right? So this works in this particular case. If this were to have an else, right, this else would bear on this if up here, and I wouldn't be able to, like this pertains to this condition, not this condition, and not the condition of both this condition and this condition. It is only an alternative if this in particular is false, right? So if you have an if and an else, you can't do this. So it's only if you have a single solitary if as the only item within another if, right? Then you can translate it as an and you'll develop an eye for that over time. And same deal with this one as well. This is a single solitary if inside of another condition, so we can turn this into an and as well. Now this is a super long, kind of annoyingly long line, so I can break these ands out like this and spread this condition head across a few lines. There's a way of doing this that is a syntax error, and I think this was the way that works. Oh no, so this is the syntax error way. Is it the other way? No. So if you get this syntax error, if you break out your code like this and you're trying to space it out and just break it out a little bit, if you want Python to ignore a line break, you can put a backslash at the end of the line and make sure there's not a space or any other code after it. Just it has to be right directly before the line break. And what this will tell Python is yes, I broke that onto a different line, but just ignore it. Just pretend like it's one line. So it'll tell Python to pretend like this is all one line. I actually liked it better with the space there. So I can get around it like that. And I like to lay this out like this. When I see this if and I know that I have like a compound condition where I'm checking all three of these things. So this is nice flatter code. It doesn't work any different than the other code, but it's a little more conventional. It's a little prettier. It's a little less deeply nested. So just a slight variation on that. Something to think about. Cool. All right, I think we got that one down pretty good. Breakout 3. Looks like we got some code in here. You're right, yeah, it's part of the language specification. Yeah. I love Python. I love that they do stuff like that. There are other, I'm getting confused because there are like other unofficial ones as well, which are, some of them are kind of funny. We got a comprehension solution in there, yeah. Yeah, it's always fun if you can, I always recommend with comprehension solutions, like solve the problem with a for loop and then go back and turn the for loop into a comprehension, which we can do that. I'll demonstrate how I would do that if we have time at the end of the class today, but this looks like we're going to be kind of up against it. So let's create another function that sorts. This isn't a true sorting algorithm, but it will rearrange elements in a string that orders or sorts a given string where each word in the string contains a single digit number. So this one's kind of funny. This is kind of an odd problem. It's kind of a very weird problem, but it uses a mechanic that is a little bit strange and a little bit particular, but it's not a common, well, depends on, I guess, on what you're doing, but it's a useful mechanic to know about, even though it we haven't talked about it too much. It has to do with sorting lists of tuples or collections of collections and what the behavior is there. Might not be quite intuitive, but we'll talk about that. So this number can be in any position in the word, and should have the word should have in the result. Okay. Numbers can be 1 through 9. So the first word will have a 1, not a 0 in it. And if the string is empty, return an empty string. The words in the input will contain only valid consecutive numbers. Okay, cool. So let's look at this. So we can understand this by its sort of inputs and outputs here, right? So it's saying this string is with a 2 in it, this with a 1 in it, test with a 4 in it, A with a 3 in it, should turn into this is a test, right? So the number that appears in a random place in the word will tell us the position that that word should have relative in the sentence, right? So this has a 1 in it, so it goes first. Is has a 2 in it, so it goes second. A has a 3 in it, so it goes third. And test has a 4 in it, so it goes fourth, right? So it's a little bit odd here. So we're going to call this one order. Oops. Print order. Okay, and do this again, print order and print order. I'm going to try to kind of align these so we can see the difference between the input and the output. All right, cool. So let's define def order. We'll take in text, some weird text, and it'll return ordered text. Well, let's do this. I want to say text in and text out. Oops, txt out. And I'm just going to assume this is an accumulator. I actually don't have to reconstruct this every time. I think I need to change this actually, but I'm just going to start with a vanilla accumulator like this. If memory serves, I need to change it. I think it needs to be a list, but we're about to discover the need for that. The reason I'm saying this, by the way, is I want to make it clear what I do need to know when I start solving a problem, and then what I don't care about, right? So I actually don't care about whether this needs to be a list or a dictionary or whatever at this point. I will discover the need for what my accumulators need to be as I continue. So for now, I'm just trying to get a good scaffolding so we can get started, right? So the first thing is we want to iterate through all the words. So we have a string, and I want to iterate through the words. So I'll say for word in. Anybody remember how to iterate through words? Will I paste the test data? Yes. Sorry about that. Let me get that in right away. Oops. This is something went wrong. Oh, that's what. Okay. My highlighting was messed up and I didn't see why at first. Apologies. Let me paste in my tests into Slack here. There you go. All right, so go ahead and either write those in or copy paste them in, and think about how we can iterate through the words in a string. You're welcome. Thanks for reminding me, by the way. So the question on the table is, how do I iterate through the words of the string, right? So I want to, well, you know, for this first test, if I print word, the first thing it should print is with a 2 in it. Oh yeah, go ahead and throw in your answer into Slack. Sorry if I didn't make that clear. Oh, sorry, we're short on time. I'll move us forward here. So apologies. This will be text_in.split. Convert to the string to a list with split. Yep, and split will divide the string at a selected character. unless we don't pass it anything, then it'll divide it on white space, which is spaces, new lines, and tabs, which are actually all the delimiters of words. That's how in English and most other written natural languages, we delimit the beginning and the end of a word by just putting space in between it. Whether that space is a single white space, or whether it's a line break, or whether it's a large tab character, in Unicode and in human languages, it's all the same to Python, right, with split. So we want to split on words. So if I just do text.split, that's going to give me a list of words by default. So let's just run it and prove that that's what happens. I should see the words in the order that they're in the thing. Okay, cool. So now, get rid of that. Now what can I do? And I'll give an answer here in a second, but I want to give you all the opportunity to think about it. So I have to discern what? I have to discern the number in the word. Right? So in order to discern what number is in each word, I have to loop through the characters of the word. So I can say for character, I'm just going to say ch in word, and then I can say I wanted to. Remember, I'm the object on the table is to determine what number is in each word. And again, we're assuming a high degree of user responsibility, that every word has a number in it, et cetera, right? In reality, obviously, you'd want to do more steps of verification, but we're not worrying about that for now. So we could say for the character in the word, we want to know if the character is a digit. Fortunately, if ch dot is digit is a method for strings, and it tells you whether the string that you're calling it on, true or false, is a digit or not, right? So this is a condition sufficient on its own, right? So if ch.isDigit will give me true or false back, and remember, a condition is any expression in Python that evaluates to true or false, right? So ch.isDigit gives me true or false back, so I can use it to tell me if it's a digit or not in my condition. And then let's just print ch to just verify that. And I want you to use the same, when you're going about coding, right? Try something out and then see, did that do what I expected it to do? And we can look 2, 1, 4, 3. For the first one, this has 2, 1, 4, 3. So that looks good. And then 4, 1, 6, 3, 5, 2. And that's the order that they appear here. Okay, cool. So we're able to determine each digit. Now, here's where things get a little tricky. And here's where I remember what I wanted my accumulator to be. Top list. Top list is equal to a list. And I'm just gonna push us through this since we're a little short on time. So there's a particular behavior that occurs when you sort a list of tuples, actually a list of lists or a tuple of lists, whatever. If you sort a collection of collections, particularly we tend to think about this as a list of tuples. But I think any ordered collection of ordered collections, I think this applies to. And you can think about what behavior would you expect? If I sorted a list of tuples where each tuple contains the number followed by the word with the number in it, what behavior would you expect? How would you expect Python to determine how to sort a list of tuples, right? So keep that question in your mind, and we'll get to that in a second. What I need to do first is create this tup list, right? My list of tuples. So if ch is a digit, I want to tup list dot append my tuple. And I'll give us some space so it's clear where the tuple begins and ends and where the parentheses for append begin and end, right? So my tuple is going to be int of ch. So it'll be the integer version of the character, which I know is a digit. I've already determined it's a digit, so it's safe to run int here because it'll work since ch is a digit, since I've already determined that, right? And then I want to append the word as well. We can also break, and this will just stop looping, like we found the digit in the word, and this will just stop this inner loop, right? Break pertains to the loop that it is most immediately inside of, right? So it's not going to break my outer loop. It's just going to break the first loop. It's going to kind of bubble up and break the first loop that it can find. So it'll break this inner loop. Okay, so if ch is digit, we'll say tuplist dot append a tuple with the integer version of the character, which we know is a digit, can be converted to an integer, and the word is the second element of the tuple. So I'm more interested in what happened to tuplist, so I'm just gonna return that for now and just see what it is. A lot of times I'll just keep something that I'm interested in monitoring at the end of the function. I'll keep that as the return until if I don't yet know what my return is, but you could print it off after the loop too, whatever you wanted to do, but I'll just return it. And let me just pare down to one test for now to get a little bit simpler output. Okay, so now we have a tuple with an integer describing what position it should go in and the word with the position, right? So if we could arrange these tuples based on the first element, that would put the elements in the right order. And then we could go through and extract just the words into a string and we'd be good to go. Okay. So fortunately, when you sort, and I'm just gonna bring this in, right? So we can actually look at it. This is that particular behavior that I was talking about. When you sort a list of tuples, the sorted function will look at the first element, and that's it. It will consider the first element as sort of I use the word handle for it to sort against, right? It doesn't take into consideration any of the other elements, but it does sort the whole tuple, right? So it'll see this one. It'll see this tuple that starts with a 1, and that's the lowest element. So it'll put this whole tuple, including this part, in the front, right? So it'll move this into the front. Oops, I knew I'd mess that up. Okay, there we go. So it'll move that whole tuple into the front, right? So this is an important behavior. It's a very particular thing. It's a very kind of weird niche thing that doesn't come up super often, but it's a good behavior to just memorize that this is how it works, right? So remember that that sorting a list of tuples will sort against the first element in each tuple, and that's it. There are times when this comes in very handy. Okay, so Oh, and I suppose we could prove that that's going to happen by just running this code, and we'll see the sorted version. Oh, of course I didn't print it. So let's do that. We'll print it out and we'll see it. Okay. So now what I want to do is extract just the second element, so the words, from each tuple in the list. So what I can do is for num and word in sorted tup list. And actually what I want to do is make a new list. I'm just going to call it list for now. Just reading the questions. Sorry, just catching up on questions. Oh, it looks like everybody's good. At me if you have a question that you want me to answer, but I'm not seeing anything at the moment. But okay, so I'm just going to start this as an empty list for now. And notice, you know, for some of you, this might look familiar if I do, like when I do enumerate. When you do enumerate IDX and element in enumerated sum list, right? You do these two elements. So don't be misled here. Sorted does not allow, it's not sorted, the sorted function that allows me to do this. It's the fact that sorted is sorting a list of tuples, and I can unbox each tuple in the for loop. This is exactly how enumerate works as well. So enumerate gives you back a tuple each time through the iteration, and it's a tuple of the index followed by the element of the list or the collection that you're enumerating. So if that syntax looks familiar, that's why. And that's how, hopefully this shows you a little bit about how enumerate works as well. So for num and word in tuple, I'm just going to say list.append word. Right, so now I've got a list of words. Oops. Okay. So now I'm interested in list. I'm going to return list. So this is a test, right? So I've got all the strings in the correct order, but they're not, it's not returning a string yet. It's still returning a list. So what I'm going to do is we're going to say string dot join list, and we'll just put a space in it. Had to beat me to it, didn't you? No, nicely done. Nicely done. Cool. So this is a test, and that is a joined string. So let's run our other two tests here. Oops, and let me just comment that out. This is a test, and for the good of the people. Cool. And then we're getting this empty line here, but we can presume that that's an empty string as it should be. All right, and it looks like I didn't even end up using my text out variable here. Let's see where I used text in, just there. I'll just call that text. So just come back and clean things up a little bit. Nice. All right, we're pretty close to wrapping up. I don't think we need to go through the, or we don't have time to go through the comprehension versions, but we can just wrap up a few minutes early today. This is going to be the last day that or the last Python class that I'm teaching. Tovio and I will co-teach next Monday. Next Monday, or this coming Monday, will be the final class for this go around. If you're interested in attending the next premium prep, since you're in this one, it's free to just defer into the next one. Just in case you didn't know that, just let Tovio or I know if you want to be in the next one, and we'll send you the deferral form, and that'll just ensure that you're on the list to be added to the next one if you want to do that. Yeah, so it's been a lot of fun, and I will see you on Monday. Tovio and I will co-teach that, although Tovio will lead. It's been a lot of fun working together, and hopefully I'll be seeing y'all around some more, maybe in interviews. And if you need further help or further support outside of this, don't be a stranger. Don't hesitate to reach out. I'm available for like one-on-one mentoring. If you're interested in that, just DM me and let me know. Cool. So we'll wrap up there. Have a good rest of your evening, and I'll see you around later. Oh, also stay on for questions if you want.